Lewis structures are a common tool in chemistry when we're talking about molecular compounds, compounds that are created through covalent bonding. We can make a sort of a picture of that molecule. It's not a very accurate picture in all cases, but it gives us a strong hint about what its structure might be because it describes the electron arrangement in a molecule or a polyatomic ion. Now, by electrons, we really only mean valence electrons. There are a lot of electrons in some of these atoms that never take part in chemistry because they're inside. They're not in the valence shell. They're not in the highest shell. But we're going to describe where these electrons are for every atom in a molecule or a polyatomic ion by using Lewis structures. In Lewis structures, lines represent shared electron pairs or bonds, and pairs of dots represent unshared electron pairs, or what we call lone pairs. And even though some dot notations have single electrons, like oxygen, for example, has this dot notation where there's a single electron on the top and a single electron on the bottom, you're never going to see that once bonding has taken place. In a Lewis structure, no single electrons. They're always in pairs. Sometimes that pair is a stick, like in water. Two places oxygen's pairs would be bonds, and sometimes they're lone pairs. Two of the electrons on oxygen in water are lone pairs, but they're always going to be a pair, never a single dot once you draw a Lewis structure. Here are some examples of Lewis structures. For hydrogen gas, we see one bond, and that's it. For chlorine gas, we see one pair that's a bond, that's the shared pair, and then each of the chlorines has three lone pairs or unshared pairs that are shown by pairs of dots. Stability is still maintained. There's still 8 dots around each chlorine. One of the pairs of dots just happens to be a bond. Another example is ammonia. Ammonia has a pair of dots and 3 shared pairs. That's a total of 8 for nitrogen. So that's stable. And then water we already looked at. So how do you make these Lewis structures? Well, there's a set of rules, and most of them are pretty easy rules. There's only one that's a little bit hard to get at first, but with experience you'll come around. The first thing to do is draw the electron dot notation for each atom that's in the molecule. Now, this is easy to do because whatever column it's in, remember, that's how many dots it gets. So if I'm going to do ammonia as an example, I would draw nitrogen. It's in column 5. Remember, I put a dot on each side before I double up. So 4 dots there and then 5. So there's the dot notation for nitrogen. And then hydrogen, 1 dot. And I have 3 hydrogens, so 3 of those. Now the next step is going to be add up the total number of valence electrons that are available. So in this example, I've got 3 hydrogens with 1 dot each, so that's 3 electrons. And then nitrogen has 5 dots, so I'm going to have a total of 8 electrons. The next thing you're going to do, once you have your total, which for us was 8 electrons, you arrange the atoms in a skeleton structure. So forget about dots for a moment and just stick the symbols for the atoms in some kind of a skeleton structure. So how do you make this skeleton structure? Well, here are a few hints. One hint is the closer an element is to the middle of the periodic table, the closer it is to the middle of the molecule, typically. So if you look at the periodic table, in this example, nitrogen is closer to the middle of the table than hydrogen is. Hydrogen's right on the edge, so nitrogen's probably going to be in the middle of this structure. Another hint is that typically in a binary compound, that means a compound that's made of only 2 elements, the one that's listed first in the formula is usually the one that's in the middle. That's not always true, but often it is. Hydrogen can only have a full duet. It can only have 2 dots, and that's 1 bond. So hydrogen will never make more than 1 bond, so you can't have hydrogen, for example, bonded on both sides, like a hydrogen bonded here and a nitrogen bonded here. You can't do that. Hydrogen can only make 1 bond, so it has to be on the outside of a molecule. And dot notation gives us a hint about how many bonds are likely to form for the different nonmetals. Things that are in column 4, for example, like carbon, their dot notation looks like this. There are 4 spots for sharing to occur, and so carbon will typically make 4 bonds. Nitrogen has 5 dots because it's in column 5. Well, that leaves 3 places for bonding to occur, for sharing to take place. So nitrogen, typically when it bonds, is going to bond in 3 places. So skeletons with nitrogen in them often are going to have 3. Oxygen Oxygen's got 6 dots. It's 2 places for bonding to occur, 2 lone dots. And so oxygen will very often bond this way, 2 bonds with 2 lone pairs. And column 7s, like fluorine, have 7 dots. So that means there's 1 lone dot, 1 place for sharing to occur, and so halogens, like fluorine, are going to typically make 1 bond. Now these aren't hard and fast rules, they can be violated, but when possible, these are the bond structures that you're going to try to make in your skeletons. And another hint is that molecules tend to be compact and symmetrical rather than long and stringy. So for example, if I had CCl4, this skeleton with the C in the middle and the 4 Cl's arranged around it is a better structure than carbon in the middle and then a Cl and then a Cl and then a Cl and then a Cl. Those long stringy things tend not to occur, and more compact and symmetrical things tend to occur more. So going back to ammonia, I want to make a skeleton structure that has hydrogens on the outside. I know that nitrogen tends to make 3 bonds, and so it's kind of a natural thing to just draw nitrogen in the middle surrounded by the 3 hydrogens. Once you have a skeleton structure, your next step is, now we start worrying about dots. You already have some electrons in the structure because the skeleton includes shared pairs. That's what the sticks are. Next, you add pairs of dots, never single dots, but pairs of dots, until each atom has a full octet, except hydrogen, of course, which doesn't need one. So in our example, this is the skeleton that we have. Nitrogen doesn't have a full octet. This bond makes 2 electrons. The next bond is 2 more, so that's 4. Third bond is 6 electrons total, but it needs 8. So I'm going to add a pair of electrons on this remaining side. A good way to think about this is just imagine a box around every atom. That box should have something on all 4 sides, either a stick or a pair of dots, and that's a quick shortcut to writing in the correct number of dots. And the last thing you want to do is make sure the number of electrons in the structure matches the count that you had in the first place. So when we counted up all the valence electrons that were available, we found we had 8. If I look at my structure, I find that I also have 8. 2 here, 2 here, 2 here, and 2 here. That's a total of 8 electrons. Now at first, that count is always going to go right unless you did a mistake. But in the future, we're going to find out that this is actually a valuable diagnostic tool that can help us figure out if we need to modify our structure so that it matches what the molecule is really like. So let's draw another example, water. First thing I want to do, remember, is I want to draw the dot notation for all the atoms that are in my compound. So 2 H's, and then I have an O. Next I want to count the valence electrons, count all the dots. Oxygen's got 6, plus another 1 for hydrogen, plus 1 more for the second hydrogen. So that means my structure, when I'm all done, should have 8 electrons in it. Skeleton. Well, I know oxygen prefers to make 2 bonds because it's in column 6. Oxygen's closer to the middle of the table, so it should be closer to the middle of the molecule. And also, hydrogen has to be on the outside because it can only make 1 bond. So there's the skeleton that makes sense. Now I have to fill in dots. Oxygen does not have a full octet right now. It has 2 electrons in 1 bond, 2 electrons in another bond. That's only 4. The other 2 sides of the box still need electron pairs, so I put pairs in dots. Now everything's stable. I just count to make sure I have 8 electrons, and I do. 4 of them in bonds, 4 more in lone pairs, so that matches my 8 electrons. So the Lewis structure for oxygen will look like what we've drawn here, just like that. This is called carbon tetrachloride, CCl4. Let's draw a Lewis structure for this. Carbon's column 4, that has 4 dots. Chlorine is column 7, that means 7 dots. Now, I could draw 4 chlorines, but they're all going to look the same, so I'm going to take a little shortcut here, and I'm going to say 4 times however many dots I have there. So chlorine's got 7 dots. 4 times 7 is 28, so there are 28 electrons there. Plus, carbon gives me 4 more electrons, so the total is going to be 32 electrons in my structure. Next, I make a skeleton. Now, I know that carbon is a column 4, and it tends to make 4 bonds, and chlorine is a halogen, and they tend to make only 1 bond. So here's what makes sense. I'll make a compact symmetrical molecule by putting the 4 chlorines on the outside and the carbon in the center. Now I have to make sure everything's stable. Carbon is. 4 bonds make 8 dots, and so that's already stable. But the chlorines, if I think about a square around each chlorine atom, 3 of the sides don't have anything on them, and so that means I need 3 more lone pairs to make a full octet. So on each chlorine, I'm going to place 6 dots in 3 pairs to give them stability. Now everything's stable. I have to make sure that my structure has 32 electrons in it. Each chlorine is surrounded by 6 electrons in lone pairs, and there's 4 of them, so that's 4 here, 4 here, that's 8, 4 more here, that's so that's 6 here, 6 here, that's 12, 6 more is 18, and 6 more makes 24. So that's 24 electrons. Now if I count the bonds, 26, 28, 30, and 32. So I do have 32 electrons in my structure. So that's the structure I end up with. Okay, you try one. Stop the video and follow the steps and try and draw the Lewis structure for CH3Cl, which is called chloroform. Okay, here's your solution. Carbon, 4 dots, hydrogen, 1 dot, and chlorine, 7 dots. But I have 3 of them. So 3 times 7 is 21, plus another dot for the hydrogen, plus 4 dots for the carbon, and this all adds up to 26 electrons. Skeleton structure. Well, I know carbon wants to have 4 bonds, so I'll put that in the middle. It's also closer to the middle of the table. Hydrogen has to be on the outside, and chlorines, like all halogens, tend to want to be on the outside, so this is a skeleton that makes sense to me. Now I have to fill octets. Hydrogen's already okay. Carbon is too, because 4 bonds is 8 dots, but the chlorines have 3 sides that are empty, and so on each of those 3 sides I'm going to put a lone pair. 6 more electrons on each chlorine gives them a full octet, so now everything's stable. Now I count. 6 on one chlorine, plus 6 on the second chlorine, plus 6 on the third chlorine, makes 18 electrons in lone pairs. And then the 4 bonds is 8 more electrons. 18 and 8 is 26, so my structure is good. Try this one, CH3OH. This is methanol, or methyl alcohol. Here's your answer. First I draw a dot notation. Carbon has 4 dots, because it's group 4. Hydrogen has 1 dot. And this time I have 4 of them. 3 of them are clustered together here, and then there's one that's hanging off by itself, but 4 total. And then oxygen's in column 6, and column 6's have 6 dots. So 6 plus 4 times 1 plus 4 for the carbon. When I add this all up, I've got 14 electrons in my structure. Skeleton. Carbon, 4 bonds. Oxygen wants to make 2, so maybe I'll hang that oxygen here and attach a hydrogen to it. And then that leaves me 3 more spots for my remaining 3 hydrogens. You can sort of get an idea of why they made that formula the way they did. By hanging that OH off to the end, they give you a hint as to what its skeleton structure should be like. Everything has a full octet except for the oxygen's not okay. It needs 2 more pairs of electrons, and so I'll put them in on the open 2 sides. Now I count up. 2, 4, 6, 8, 10, 12, 14 electrons. My structure's good. Try this one. C2H5OH. Everybody's favorite alcohol. Okay, now I have carbon, 4 dots, but I have it twice this time. Hydrogens. Now I have 6 hydrogens, 1 dot each. And I still have an oxygen, column 6, so 6 dots. So let's add them up. 6 electrons here, 6 electrons from my hydrogens, and 2 times 4 is 8, so 8 electrons from my 2 carbons. This gives me a total of 20 electrons. That's how many should be in my structure when I'm all done. Now I'll make a skeleton. I have a carbon here. I'm going to make 4 bonds around it. I'm going to try another carbon, making 4 bonds to that. And I think I can do it, because if I put an O here, which prefers to make 2 bonds, followed by an H, that O is going to be okay. And I still have spots for 5 more hydrogens, and I have 5 more hydrogens in my formula, so that's where they're going to go. The 2 carbons have full octets. The oxygen doesn't, So like in the last example, I have to put 2 pairs, and that's commonly going to happen with oxygen. Now I'll count up. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 electrons. My structure is good. Here's a structure that some of you might have started out with. By putting the oxygen in the middle and the carbons on the outside, you might think, okay, O's making 2 bonds, carbon's making 4 bonds, but then you have an extra hydrogen you have to put in there somewhere. Now you can put that hydrogen in there and then fill the octet and count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. It's the correct electron count. So why wouldn't this one be okay and the one that we actually drew is okay? Well, the one that we drew has oxygen making 2 bonds. This structure has oxygen making 3 bonds. And so this isn't the preferred structure. It doesn't follow the pattern that molecules actually follow when they form. C2, H2, F4. Give this a try. 2 carbons. Each one has 4 dots. 2 hydrogens. Each one has 1 dot. And then 4 fluorines. Fluorine is at column 7, so that means 7 dots. 4 times 7 is 28, plus 2 for the 2 hydrogens, plus 8 for the 2 carbons. Well, this gives us a total of 38 electrons that we should have in our structure when we're done. I have hydrogen and fluorine in here, which are probably going to be on the outside, and 2 carbons. So I'll stick the 2 carbons to each other and put enough sticks on them that they can each have 4 bonds. Now I'm going to try and make this symmetrical, so I'm going to balance my hydrogens by putting 1 on each side, and I'm going to balance my fluorines by putting 2 on each carbon. Now I fill octets. Okay, hydrogen's good. It only has a duet, and it's satisfied now. Both carbons are surrounded by 4 bonds. That's 8 electrons. But the fluorines each have 3 open sides, and so I'm going to fill those open sides by putting pairs of electrons on each side. Now I got to count. Fluorines have 6 lone pairs. There's 4 of them. 6 times 4 is 24. Now if I count at the bonds, 26, 28, 30, 32, 34, 36, 38. My structure is good. C6H14. 6 times carbon, carbon's 4 dots. 14 times hydrogen, hydrogen's 1 dot. So let's add them up. 14 electrons here. 6 fours is 24. 14 and 24 is 38 electrons. Now I'll make a skeleton. And well, hydrogens have to go on the outside, and this sort of forces me to just make all 6 carbons in a row. And then I'll see if I can attach 14 hydrogens. Each carbon making 4 bonds, there would be 3. And the rest of these middle carbons are going to have 2 bonds each, so that's 4, 5, 6, 7, 8, 9, 10, 11, and this N carbon has room for 3 more hydrogens, and that makes my total of 14. Everything has a full octet. All carbons are surrounded by 4 bonds. And if I count up the electrons, they're all in bonds, so it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38 electrons. There's my structure. One more. Draw the Lewis structure for PBr3. Phosphorus is a group 5, 5 dots. Bromine is a halogen, group 7, so that means 7 dots. And there's 3 of them. 3 times 7 is 21, plus the 5 from phosphorus gives us a total of 26 electrons that we should have in our structure. Skeleton. Well, halogens prefer to be on the outside. Phosphorus is a column 5, and they tend to make 3 bonds. So what makes sense is I'll put my 3 bromines around my phosphorus and then fill octets. Phosphorus has 3 bonds, that's 6 electrons. One side still needs a pair. Each of the bromines is only making 1 bond, that's 2 electrons. It needs 6 more, and so on the remaining 3 sides I'll put a pair on each side. Now I'll count up my electrons. 6 on this bromine, 6 on this bromine, 6 on this bromine. That's a total of 18. This lone pair makes 20, 22 for this bond, 24 for this bond, 26 including this bond. There's my structure. Well, as you draw more and more Lewis structures, you'll get better and better at it, and pretty soon you'll be able to draw a Lewis structure for almost everything. Later on, we're going to find out that they're not always this simple, and you might have to add some features, but you'll have good clues about when to do that.